recording. Yes, from now we are recording this webinar and then we will publish it in our website. So as all the software, we can go to File, Open, and New Study, or we can save like all the Windows-based software. But how we can model a network? Before modeling a network, I want to show you that how we can make it more simple. So if I go to here, I go to customize toolbars. There are some toolbars unnecessary for industrial, because now we are talking about industrial. For example, find, color coding, maybe this editor tools is not necessary. Display, here you can see display also may not be necessary because it's for distribution. Analysis, we have analysis here, you can have analysis here. Let's see which one. I can have both, but for now I remove it. Tooltip may not use it. Load model is for distribution. Database is for distribution. I don't need database, you see. Advanced editor tools. Advanced editor tools mostly is for distribution. I don't need it. Drawing tools for distribution. Zoom is for distribution. Page layout, we can use it. Page layout. Let me remove it. We can have also have this here. Symbol layer, we don't need it. TCC is for coordination, we need it. Control plot, meta, Python, we don't need it. Okay, Mr. Okay, let me mute him. He just arrived. Let's mute him. Okay, thank you. Mr. Thurs, if you have any question, you can put your question and chat menu. That's it. So mostly these menus are for distribution, because the same software, basically this version was used for distribution, for more the utilities, but now it's also proper to be used in industry. I will show you. Then we have this Explorer bar. Also, I will go to View, Explorer bar. Something I don't need it. Database, it's for distribution. Database does not mean the library. It means the database equipment will go to the database. Configuration will go to the database, and you can edit it from the database. It's not good for industry. I remove it. I don't need charts. Switching monitoring for distribution. Search, we have search already there. But what remain? Also abnormal condition, we have it here. What remains is the minimum, and it's not something big. We can remember this. So we have symbol bar, Explorer, study project, and display. That's it. So I go to symbol bar. I want to model very simple network, 11 kilovolt by 0.4 kilovolt, and do load flow short circuit, and then do motor starting and do coordination in maximum 45 minutes. So first I drag and drop a source. This source, I put a name, source 33 kilovolt. Okay, I can have the source from database, but I put it user defined, and I put the equivalence, this 33 kilovolt. The voltage can be unbalanced. Okay, in industry mostly I have balanced voltage here. Short circuit level, I can have equivalent impedance or short circuit level. I have short circuit level. Suppose that for 33 kilovolt is let's say 25 kilovolt for 3-phase, and for 1-phase is 9 kilovolt, and X over R is 10 and it's 8. Okay, so I have equivalent short circuit here. So I model this. This is the source. Very simple. I can zoom by a scroll. Also, if let's remove this guy. Also here, it is for coordination. Okay, I put it here. Okay, and I put it here. Make it more simple. Okay, also I don't need this guy. I put it here. I want to make it more simple, and this is for coordination. Coordination. Okay, that's okay. Let's put it here. So now I want to show you other facilities we have inside SIME. We have here display, show alignment, we have show alignment, show link, we have show link, show zoom, pan and rotate control in view. So when I click on this, you can see all of this. So if you don't have a scroll or you don't use mouse, you can use this, and from here it will be more simple to do it. Okay, let's go to modeling a network. Now I want to model a network. First, see, I have a transformer. After this, before transformer, I have a cable. So I go to a cable. Very simple. This is cable. Drag and drop it here. Then from this cable, I have a transformer. I go to transformer, two-winding transformer. But I think this was, yes, transformer biphase. Inside we have transformer biphase, means single phase transformer or transformer. I think for industrial we have to remove this single phase transformer. Okay, I have a transformer, and then after transformer there is another cable. Okay, then here I have a breaker with relay. So I go to this switching breaker, and this is relay control breaker. Okay, this is relay control breaker, and then here I don't need to put a bus bar. I convert it to bus bar, extend it here, and then I put another relay control breaker here, and then I put one LV circuit breaker. So LV circuit breaker is this, and then I put cable, another cable, and a load as well. I will put a load here, and here let's put induction motor. That's it. Oh, we can put a cable as well. Okay, and then I put induction motor. So as you can see, I have a network here, includes 33 kilovolt. Then there is a cable. After transform, there is another cable. I have a relay here, another relay, but I think here I have to delete this guy and put relay upstream. Okay, here we have two. Okay, now this is my simple network. I have to first I have to have all the data from the library. But if you don't have the library, what you can do, you can prepare the library by yourself. But SIME that has library, and we can include it. But now I want to show you how to add library to SIME. Suppose that I have a transformer. I want to go to a transformer. This transformer, add the transformer is 33 by 0.4, 15 kilovolt. And the rating, suppose that this is 10 megavolt ampere. No, excuse me. It will be 2500 kilovolt ampere. Okay. So it will be three phase Y delta YG. It will be 2533 and is 0.4 15 kilovolt. And the impedance percent, we can estimate the impedance. Okay, this is distribution transformer. That's it. It's up to load center transformer. So you can estimate the impedance here. It could be high, low. It's based on this, we can estimate the impedance here, or you can have the impedance by yourself here. That's it. You can use the estimate here. Suppose that this is something like 4% according to catalog as my experience. Okay, now we have this transformer. If I go here, I can select it here, and all the data comes automatically to my network. Okay, for the induction motor, also I can use. I can go to SIME and show SIME library. Of course, I can show SIME library. SIME that has a library, you can use it, and you you can use the SIME library here. But if you don't have a library, I want to show you how simple we can add an induction motor to this network. Suppose that my motor is 4.14 kilovolt and the rating, suppose that is 400 HP, okay, or 400 kilowatt, doesn't matter the value, I don't care. So I go to 400, okay, and the voltage is 415, that's it, speed is 1500, and then here, like rotor data, 25 power factor, I select F or G, like rotor data, and like rotor current is, for example, 6.1 times. What I need equivalent circuit. Equivalent circuit here, we have to calculate equivalent circuit. Let's one of the people, okay. Now we have to calculate equivalent circuit, but inside we can calculate equivalent circuit for induction motor. Very accurate, but very simple. How we can do it? Previously, SIME had some methods for estimation equivalent circuit, but recently in SIME 7.2 it added two methods. We can calculate equivalent circuit and K/H factor. We can calculate it from the nameplate data. We can calculate it from performance characteristics. That is the most accurate. But okay, now we will calculate it very simple through nameplate data. So I go to nameplate data, the data automatically comes. What you have to change is only operating asleep. Okay, suppose that operating asleep is 1%. So immediately it's calculate and it calculates K/H factor. K/H factor is what other software doesn't have it or does not consider it in the calculation. Okay, now I have this equivalent circuit, and then I open induction motor and select it, and all the data comes automatically. That's it. This is for induction motor, and then for the load, I open. Load can be balanced or unbalanced. I change it from unbalanced to balanced, and I have kilowatts. Suppose that this is 800 kilowatt, and the power factor is 80%. That's it, nothing more. So now I have this motor. I saved in my file as a webinar file here. Webinar. Okay, today is 7th of October. Now I save it. Now I have to calculate the cable, or I can take these cables from library. I don't want to do it from library. If I go to SIME library, there's a lot of cables there. I don't know who this voice is coming from, who. Okay, so if I go to library, I go to cable, and here if I see there's a library from SIME. So SIME that has a library for 1 core and 3 core cables, but we don't care about it. We want to calculate. We want to create a new cable because we want to talk about something important. 1 core cables, you can't use impedance from the catalog. It's impossible because for 1 core cable, impedance and resistance of cable are due to installation. If you don't care about installation, the impedance will be wrong. I will show you right now. This is the main purpose of showing you calculation in SIME. Let's add a cable. Suppose that I have a 33 kilovolt cable, and it's let's say 300 millimeter square, and it's 1 core, XLPE, and copper. Okay, so I have 33 kilovolt. For example, manufacturer is Ducab, standard is IEC, and I have 1 core cable is copper. I go to 300 millimeter square, and I can design the cable. This is a 1 core cable. The cable consists of sheet and the maximum is 32 millimeter. I don't care about concentric neutral. I don't care about armor, nothing. So I have one core cable in 33 kilovolt. And if I go to impedance, you can see impedance here, because impedance shall come from construction detail. It can't come from catalog. It's impossible, because if the impedance comes from catalog, how catalog can predict where you are installing this cable, because it's a single core cable. Let's show you. So we have this cable, one core cable, 300 millimeter square. If I go here in this cable, I select the cable here, it asks me installation. What is the installation? Installation, it can be flat touch, flat space, it can be trefoil. Let's calculate it. Let's check it. Okay, I want to show you the difference between configuration and the impedance. Okay, let's see. Now the configuration is trefoil. If I go to equivalent impedance and calculate it, let's keep these values. I have to go to this Windows accessories, snipping. Okay, and then I will open a file in Word as well, Office, and I will open Word 2002. Okay, so now I want to show you what is the configuration. The configuration is trefoil. I will make a picture from trefoil. I put it here. So, and the impedance, I will make a picture from the impedance. Okay, so the impedance, equivalent impedance, it will be this value. I don't care about the value, because later on I want to compare this value with the previous one. That's it. This is the value. Then let's come back to the cable. I want to change the installation from trefoil to flat space, and the spacing we put 15 centimeter. That is something very normal. 15 centimeter is very normal, so I consider this installation. That's it. I put it here in the next page. Okay, not next page. Let's go to the next page. Okay, and then I want to show you the impedance. If I go to impedance, you can see now the impedance. I can check positive sequence impedance is 0.1983. Now the positive sequence impedance is 0.086. Here resistance is 0.7593. Here the resistance is 0.78. Okay, so there's a difference. Let's put the impedance together. Let's put it there. And I want to have the impedance together. So we have two cases. The first case is when you have trefoil. The second case is when we have flat space. So the difference between the impedance is not negligible. So when you have a single core cable in any voltage level, doesn't matter. In any voltage level, you can't use catalog impedance or resistance. Okay, let me do something else for you. If I install this, I come here, I install this cable in trefoil, and I put this in magnetic duct. What do you think? Do you think magnetic duct will affect resistance or reactance? Definitely it should. If I go to impedance, now I go to magnetic duct because the equivalent will be changed. I go here and I put the values here. So you can see the reactance change. And something else important, resistance change. Why resistance change? Because of proximity effect. If you want, you can put your email in chat menu, so I can send you all the documents and standard regarding to affecting resistance of cable due to proximity effect. Okay, that's it. So we have to calculate it, and SIME is the only software in the world that has this calculation so far. There is another software, but what SIME did, they integrated this cable impedance calculation to the calculation, okay, to the analysis software. So now let's come back to the analysis. I don't want to waste the time just to explain the impedances. No. So I have this cable here. Suppose that this cable is something like 1000 meter. Okay. Then I have another cable here. This cable also is one core cable, but in LV side. I go to cable. I calculate it very simple. It will be 0.415 kilovolt. It's 400 millimeter square. XLP one core. So I put it for 15, and it's something like 800 ampere. One core 400. And I forgot to calculate withstand rating. Calculate it automatically. I change here. I don't need this sheet. I want to have a concentric neutral. Okay, concentric neutral. It will be one less than one. It will be. You can have this data from manufacturer. That's it. Okay, so I have this cable, one core cable, and it's on LV side. Okay, that's it. I want to have another cable, very small size of cable. I copy the same, but this time I want to have 3-core cable. So I copy this. It will be 3-core and 3-core cable, 240 millimeter square. That's it. So now for 3-core cable, when I select 3-core cable, this is 300 millimeter square, and that's it. So impedance computed from construction detail. So for 3-core cable, you don't need to input or enter the data from catalog. See here, SIME calculated based on this construction detail. Based on this construction detail, SIME calculated the impedance for you. So you don't need catalog anymore. And this is very close to the catalog values, very close for 3-core cable, and even more accurate. Yes, you need the capacitive. Let me, because this is a question from one of the guys. Can it calculate the reactive or reactive power of the cable, or you mean the XC of the cable? Yes, it can calculate it. Yes, definitely it can calculate it. Let's see any other question. If I didn't reply to, no question. Okay, that's okay. So now we have the cables. I select this cable. For example, this is 200 meter, and then it's one core. That's it. It's one core. Number of cable per phase. If I go to installation, number of cable per phase, 2 cable per phase. It's very important. Now it's very important. Or for example, sometimes we have 3 run of cable per phase. It's not like I'm telling you, the impedance will not be divided by 3 in this case. It should not be, and SIME will not do this. If I go to this impedance, see here, now the impedance is 0.078. If I go back in installation and put it 1, and go back, it will be 0.096. Got it? The impedance is 0.096. If I put 3 in parallel, 3 parallel means 3 core or 3 cable in one phase. So the impedance will not be divided by 3. You see, the impedance only changed 15%. And if I have 2 of them, it didn't change a lot. Because now we have concentric neutral. It's not conductor. Please. Cable is totally different from overhead line. In overhead line, we have conductor. But in cable, we have cable includes conductor concentric neutral and all the metallic parts, sheet, all are metallic parts. So the impedance cannot be calculated easily. It's very important. The impedance cannot be calculated easily. So if you have 2 run-off cable per phase, you can't divide the impedance by 2. You have to recalculate it, and SIME does it. SIME does this calculation. Okay, so now I have 3 cable. Okay, 3 cable in per phase, and the impedance will be reduced up to 0.78. This does work if you have 3 run-off cable per phase. The ampacity will increase, but the impedance will not be. What is the formula for impedance calculation in cable? I will send it to you, no problem, because now I will send it. If you put your email address, I will give you all the documents regarding impedance calculation, and it's based on IEC. If you go to, I can send all the documents to you. Okay, thank you for your email, Mr. Nihar. Okay, and now let's calculate it. Now we have impedance for 3 run-off cable, and here I have, suppose that this is 100 meter, and I have this 3-core cable that already have the impedance for 3 core. That's it. And we have motor. Now I do load flow. In load flow, we have a lot of methods, but now I want to use Newton-Raphson balance. We have unbalanced Newton-Raphson, fast decouple, voltage drop, balance and unbalanced. But most of the industrial networks are balanced network, okay? And we can have sensitivity load model. We can have load as a constant power, constant impedance, or constant current. The worst case is constant power, okay? So save it, and I want to have output report. Suppose that I have I want to have these details. That's it. And then I want to have let's see, tags. Which kind of tags I would like to have? Maybe powerful result. Okay, that's it. So it's creating the report as well. So I have this problem in my network. See, the report came. You have abnormal condition, and the abnormal condition shows you have a lot of problems in your network. So okay, let's come back to the network. What kind of problem do I have? Now you can see the voltage here 0.97, but this cable, the current passing this cable is 2968. So this cable cannot withstand this. So, and the cable is 3. Let's put it 4 in. Or the length maybe is, I don't know the length, let's check it. And the cable here is 400. That's it. Let's run it again. 0.86. I think the length, I didn't, let's change the tap changer here. This transformer also can have tap changer, but it could have an offload tap changer, 0.95. So that's it. I did mistake. Okay, now it's okay. So now the voltage here 0.91, and here 0.91, and you have under voltage here in whole network. How we can solve it? This transformer, maybe the voltage, we can increase the voltage not more than this. This is the maximum here. And this cable, most of the losses is on this cable. I think this 200 is too much for this cable. That's it. Okay, that's okay, no problem. So after this is 0.98, and we have only one problem here after this cable, and this cable length is 100 meter. Let's say it's 50, because I'm designing this without. Okay, let's put 50. After this is a sub-distribution board. That's it. Okay, overloading. We have some overloading for the breakers because we didn't define the breaker. That's it. So we didn't define the breaker here, and the voltage is acceptable here for us. Also, if I increase the voltage of here to 30, let's say for example is 2% more, 33.6. So now we don't have, just we have problem for the breakers. Now I have load flow. I want to show all these tags here, but I don't have it. What I have to do, I can import tags from other computer. So I can import very fast. You can have tags from other computer. I don't need this, guys. Okay, that's it. No problem. I can import all of them. So now you have, see, you have the tags. I have PowerFlow 001, PowerFlow 002, PowerFlow 003, and DV, voltage drop. You can see the voltage drop on the transformer. You can see here on the cables, you have voltage drop, and that's it. So now voltage drop on the cable, you can see 3.31%. Here voltage drop is 2%, and here voltage drop is 5.98%. Okay. Now I want to do motor starting for this induction motor. Okay, for this induction motor, I want to do motor starting. I will go to let's first short circuit. Let's first do short circuit. I can do short circuit, IEC short circuit, IEC short circuit, and see all the result. IEC tags. So I can have IEC short circuit for all the bus bars. It shows me. So you can see short circuit, 3-phase, peak, breaking, steady state, and DC offset for each bus bar. It can show you for all the nodes, all these short circuit values. Also, I can do short circuit here. That's it. And I can have all these values in report. Very nice report we have. I will show you. Here you can see for each bus bar, when I select it, it gives me all this initial, peak, everything for each one. Okay. Now I want to do something else. I want to put everything in one shot to report, because report is very important for us. How we can have report? Because without report, how I can deliver my job to the client? But we have a very nice report that they created in Sign. If I go to report, there is network summary. We name it complete report. So you can include topology, cable, protect device, everything you can add it. And all the input data also are here. You can include the input data, all the input data here. So when you go to report, I can add everything here, and you can see everything in one shot. But let me do something else. First, I want to do analysis for load flow and short circuit both. So when I run load flow, short circuit will be done automatically. So I run load flow and short circuit in one shot. Okay, that's it. So when I go to network summary, I can see load flow. I want to see the load flow for all the analysis will be, it can be, I can select all of them. I can select all the analysis here, short circuit and load flow, both of them for any equipment. That's it. When I click on OK, it preparing the report. Okay, it prepared the report, and there is a nice report. You can have project name, author, company, version, description, then you have a single line diagram, but okay, I should zoom out. Here there is the data, underload, line and cables, then you have load flow motors, then you have overload for lines, then you have abnormal condition, then you have data for the transformer, then you have a summary, then you have abnormal condition and the cost for losses, then you have short circuit details for any short circuit value, and for all the bus bars, load flow for the loads, load flow for line and cables, short circuit summary, maximum, minimum short circuit values, 1 phase, 3 phase, everything for each bus bar, and load flow for the bus bar. All these came in one shot. See, it's a nice report, which file, everything is nice. You can just put your logo here, that's it, and print it, deliver it to client. So now working with SIME is very simple. I don't know. Working with SIME is very simple. You can prepare the network. I think we did it in 30 minutes, and I prepared the report in one shot. So it didn't take at all. So now I want to do motor starting. For motor starting, I have induction motor. I want to start this motor. First, I want to have it direct online. So I want to start this motor. Okay, somebody asked me that, okay, we don't want to have this, we don't want to select from here. Is it possible to calculate charging current? Charging current for the cables? You mean? Let me put the question. Definitely, we can calculate charging current. Yes, why not? But we can do it after this presentation. You can continue. We can continue for you, and we can calculate charging current for cables. Yes, or over lines. Yes, this is your question. Okay. Messenger. So you can stay after this presentation, and we can continue for you. So now I want to start this motor. But somebody asked me that we don't want to see this menu. I want to have something very simple here. I go to toolbar, and in toolbar I select an analysis. In analysis we have this menu, like other software, and here I can do load flow, short circuit, load allocation, coordination. All the analyses are here, and dynamic motor start also is here. I click on dynamic motor start. I want to do starting for this induction motor. Okay, I run it. First I have to select, I want to run it. Yes, starting. I start this motor, and then I want to have voltage for buses, induction motors, and other nodes. I can have all of them in one shot. That's it. And what else I want to have? That's it. So now I have voltage of the motor. It is a new chart, and very nice chart that SIME bring it recently. So now I want to do starting of this motor using VFD. Suppose that we want to do it in VFD. I can do it from here. Assistance should be VFD. We have all this kind of soft starter, auto transformer, spring, and VFD. Suppose that we want to do it VFD, and VFD the current is 1.5 times, because in VFD you know that it controls the current by ratio of V over F, or voltage over frequency. So I can run it. Okay, that's it. I can have this voltage Vs time and compare it for this induction motor. I want to have the voltage. So you can compare these two curves. The blue curve is a starting voltage of the induction motor, and this green curve is when we are using VFD. So it can takes less time than running, because you are paying. You have equipment to control the current, and it does not take long time. Also, if I go to chart again, here I want to have all these. Here I want to have electrical torque. Let's go to new chart, electrical and mechanical. Then I want to have power factor, electrical and mechanical power, current, reactive power, speed, apparent power. That's it. So I can have all of these in one shot. Also, you can see this is torque. This is a power factor, a starting power factor, and then at the end running. This is active power of the motor, and at the end this is active power, and electrical and mechanical power for induction motor, and this is current. So it's a starting current something like 1150, and then the running current is something like 70 ampere, and then this is reactive power, and this is speed, and it reached to 1485. You can see 1485. At the end is apparent power of motor, and at the end I can close all the charts in one shot. That's it. So starting motor can be done very simple, and also we can put it in the report as well. Let's do coordination, because you have to see how fast we can do coordination inside SIME. Okay, any question? Any questions so far? If there is any question, we can go to question. Otherwise, I want to go to coordination and show you how we can do coordination inside SIME software. Okay? No question? Let me ask the guys if the guys are already there. Do you have any question, Mr. Hema, Mr. Kumar, Mr. Nihar, Mr. Rohit, yeah. Mr. Thers? No? Yeah. If you want, I can open. I can unmute you and you can ask question. Just let me know if you want to have a question. Just tell me I have a question. I unmute you. Okay? Okay. So seems that there is no question. Let's see. No question. Okay. If there is any question, put in chat menu if you have a question, and then I will come back to you and unmute you and you can ask your question. Okay, no question. Okay, let's go to coordination. You want to do coordination here. First, for coordination, suppose that I want to do coordination here, but the case is that I have one relay here, one relay here. We do both, one relay here, one relay here, and one MCCB and one relay here. So how fast we can do coordination here? And suppose that here, let's first do load flow, because I forgot what was the value of the loads here before. Okay, that's it. Here, let's go to power flow, and the current here 2100. Suppose that the rating of this circuit breaker is 3000. So let's go to this circuit breaker. How to choose circuit breaker like ACB? We choose it based on a nominal current and the short circuit. So for example, now you have 2000 something like this, the maximum load and maximum current. We select it and we'll go to upper size. So for example, now if we have a 2200 and the maximum load is something like 2600 ampere, we go to 3000 rating of ACB. And also the short circuit rating is very important for us. Okay, let's do it. I can also use SIME library. I don't want to use SIME library. It's a library for ANSI and IEC. I don't care about it. I go to, it's for example, it's X. I don't want to promote any brand. It's X brand, and it's 3000 ampere for kilovolt. And suppose that it's 31.5 kiloampere. So standard is IEC. In this area, manufacturer is X, model is Y. I don't want to promote any. 3000 rated is actually the rated voltage. It should be something like 600 kilovolt. Okay, and others I estimated, but maximum breaking, as I mentioned, it should be 31.5. That's it. And another one, I want to have for outgoing 630 ampere. 630 ampere, and the same rating, it will be 630 ampere. And another one, let's put it 800 ampere. or let's see 1600 ampere. So I have 1600 ampere as well. There is another question. There was an error for me while doing SIME. The error showed database could not be found. The reason is that before you had a database, now you remove it from your hard. So is the reason that you couldn't get. Let me put all the question. Okay, because others can't see your question, so now you can see the question. The question is that okay, the first question, it was how to calculate short circuit for bus bar, and okay, I will show you how to calculate a short circuit for circuit breaker. I will show you. You can have a short circuit for a bus bar and see all the contribution from other bus bar. Okay, this is regarding to this problem is regarding to database. You remove the database from your hard disk. You have to remove it from your SIME. I will show you. I noted. I will show you after this. Now first I want to show you coordination. Okay, now we have this. I select this guy. 3000. Oh, 3000. I did mistake here. It should go to 3000. Okay, that's it. Now I selected 3000, and this guy, it should be 1600, and this guy, it should be something. Okay, we have to have LV circuit breaker. I don't want to show any brand, but okay, let's go to one of them, no problem. What happened? Okay, now I have no choice just to show you one brand. Okay, let's go to, for example, ABB. ABB, let's say 800 ampere. NS 800 ampere. Okay, it could be solid state, model case, electromechanical. Manufacturer, it will be ABB T-Max. Model will be, let's see, ABB T7. Okay, that's it. Standard IEC, that's it. We have this. So now I want to do this coordination. This relay also, we have no way to show you. This CT should be, for example, 2000 by 1 ampere, and the neutral also, it will be 2000 by 1 ampere. And then the relay I go to, because I select the ABB, so let's just promote one of the, nothing more. Okay, let's go to ABB. Let's go to 615 and normal inverse. That's it. And then here I go to the same. It will be 3000 by 1, and neutral will be 3000 by 1. That's it. So, and the relay also should be ABB again, because we use the same. We can use another, but okay. We have 3000 by 1, the nominal current is 2200 something. We have to define this setting. Let's go to another setting for this coordination. So let's see if I go to point. No, I need something else. Tab range should be changed. Let's see if I go to these values, 0.85. No. 0.85. Okay, let's calculate it. If I calculate it, 2160 multiplied by 1.5, also will be 2376. So if I go to 0.8, 2400 is suitable. So it's the initial setting for me. Let's again do load flow here. I want to do load flow again and see the current. 1434. So okay. This is 2000 by 1. So the rating here, the primary pickup, I have to calculate it. 1460, okay, multiply 1.1, okay, 1600, something like this. So it should be 0.8, something like 0.8. Let's calculate. Okay, 1000. So this is initial. I didn't touch even time dial, TMS, nothing. Okay. Now I have to do, let's save it, branch device coordination, and I go to this relay. I want to do coordination for these two relay. Okay. I display. That's it. Okay, for now, I have this relay, and this is another relay. Do you think if I have coordination and if the coordination is proper for now? I don't think so, because according to IEC, the discrimination between these two relays, it should be at least 0.2 seconds. Okay, let's do something. Let's go here. I want to calculate, suppose that the current here 10,000. So here you can see the delta is nothing. So upstream can operate simultaneously. So okay, what can I do? If this is the end, I can use instantaneous. So I go here. So I go to instantaneous, and for 2 times of nominal current, I use instantaneous. And then short circuit, I show the minimum and maximum short circuit current here. And also I show this curve. That's it. Also I can, let's see, this is not good. Let me go to, okay, all the tags. I want to change all the tags from 10 to 20, apply to all. That's it, I can see this. Now it's okay, that's okay. Now it's okay, it was very small. Okay, now this is the cable, and also you can see the damage curve of the cable. So I have this curve. Okay, the upstream, let's again calculate it. If I go to device margin and calculate here, okay, the difference is 0.19. Still is not proper. So what you have to do? There's 2 ways. If you have instantaneous function, you mean that you have 50 function in your relay, you can use this and you can define instantaneous 0.2 seconds after operating this relay. But if you don't have it, what we can do? We have to change this. Suppose that I don't have it. So what I have to do, I have to change this TMS. So okay, now. And then what I do, I check it again for 11,500 ampere. Okay, 11,500 ampere. Let's go to 12,000 ampere. No, excuse me, 20,000. 20,000. So for 20,000, let's see. This relay is operating at 0.05. This relay operating, oh my God, it's too much. Let me reduce it. It's my mistake, sorry. So if I go to 0.08, and again we calculate it. So the delta is 0.2, but we have to calculate it at this current. So there is another tools, mouse. I go here. Okay, 3 relay. Okay, 1 relay, first relay. Okay, so I can see. So the delta is, okay, it's less than. We have to just change it. So that's it. Let's again go to, so this current is something like 20, and this is 25,000. Okay, I can see the current here from this short circuit value. If I keep the short circuit 25,270. Okay, let's do it. 25,270. I go to user defined, and no. Intersection, you can see the intersection. There is no intersection. Minimum time separation. Short circuit user defined. 25,260. Okay, so you can see delta is 0.18, so it's not proper. What I do, I go to 0.9, and if I calculate it again, now the delta is okay. But in this case, what I'm doing, I'm increasing operating time. So I'm increasing time. So here, suppose that you have this current, short circuit current can be 10,000. Yes. So this relay will operate at 4.4 seconds. Is it proper or not proper? Sometimes I don't want to have it. Maybe if the current is less, that is very possible. Let's go to this relay and go to short circuit and then do this. That's it. Okay, now you can see the short circuit value are the same because they are connected to the same bus bar. So here you can see the short circuit can be from minimum to maximum. Okay, so the short circuit maybe it be 7 kiloampere. So it operate at 0.5, 0.58. And if it be something like 4 kiloampere, okay, it operated at 1.2. That is not proper. It should not be operated more than this. So my solution is that if your relay has the function of 50, because you have 50, 51, 50 is instantaneous, you can use this function, and I can select this guy. I go to instantaneous, go to this ratio. I put it 2 point. Okay, I think 2 is okay for this case. You have to also check the overloading here, maybe. Let's see. I can put it 1 point, because overload will not happen for all the loads. It's possible. So I can put it 1 point. Yes, 1.55. We should have a margin also. And the delay, it should be 0.25. Okay. So in this case, you can see this relay will operate at 0.05 and this relay will operate at 0.25. And also, I can reduce this time dial from 0.08 to 0.05. So overloading also will have less time for operating. Let's see what's the question. Mr. Nihar. In summary, download should trip earlier than, yes, okay, it should be trip less earlier than upstream. Definitely it should not be, and the difference between downstream and upstream should be at least 0.2 seconds based on IEC, because you have delay or operating, you have malfunction, you have activating upstream. So all of these upstream should trip at least 0.2 seconds after downstream time for tripping. So it's mandatory. Otherwise, for example, if I have this, if I put it here, that I have seen such thing in many documents, believe me, they have this coordination. This coordination is wrong. It's totally wrong. If I go to this document and I calculate this, for example, 10, you can see the delta between these two is 0.1 second. This is not coordinated. This is the wrong coordination that nobody care about it. I don't know. This is the problem that you should care about it. The delta T between upstream and downstream, at least based on IEC, should be 0.2 seconds. The minimum time. IEC recommend you between 0.2 to 0.25 seconds. It should be more than this. More than 0.2 seconds, but the minimum is 0.2 seconds. So if you see this coordination is wrong. Upstream should operate at least 0.2 seconds. So if downstream, let me go again here and calculate it. If downstream will operate at 0.05 seconds, upstream at least should operate 0.05 seconds plus 0.2 seconds. That delta, it should be minimum 0.2 seconds. So now the coordination is correct. And very simple, you can do, copy this, put it in a Word file, in anything. If you want to prepare the report, oh my God, I didn't copy it. Copy to clipboard, put it here. So you can have all this curve, you can all this, you can add, let's show you, I don't know, its title maybe is Sam, you can add your logo here, your company logo here. Select your company logo. For example, I put my company logo. Okay, you can have this, that. Okay, all this is possible in this software. Okay, any question? I think the time is past because it's already past 1 hour. Next week at the same time, we will have another webinar and we continue this. We will have a review on previous load flow short circuit, and very fast we go to coordination and we continue with transient stability. If you would like to have this video, a link, we will send you a link. And let me first